on to the heat and changes of state one, just because I know a lot of people also had questions on this, and I'm just going to basically explain it. When you have the heat and changes of state problem, you're basically going all the way from A to E, the heating curve. So that's why I made this thing. So what you do is you have to hit each letter, and then at the end to find the total heat or energy it takes for that to happen, for those changes in state to happen, you add them up. So we have, if you have a solid, you're starting, at 10. We do Q equals MCAT for that one. And our C is 2.03 joules per gram Celsius. For melting, we do our delta H, which is, we use dimensional analysis for that one. That's our heat of fusion right here, which is 6.02 kilojoules per mole. And basically for the dimensional analysis ones, it'll give you, starting grams. You start with your grams, divide by molar mass, go to moles, and then you end up having your heat of fusion, your kilojoules or joules, on the very top. So it's your last box, and you just multiply across the top, divide by the bottom. Liquid, we do Q equals MCAT again, so it's like every other one. And our C for H2O, liquid form, is 4.184, which we have been using. Then for boiling, which is D, we're going to do dimensional analysis again. So we have go to, from grams to moles, 40.7 kilojoules on the top. And then our last one is our gas, which is Q equals MCAT. We use the C of the vapor is 2.02 joules per gram Celsius. So you may have to convert like as needed, because you see how some of these are like in joules and some of them are in kilojoules, but this is just how I write them out, like in the standard form. So you may have to convert along the way. And basically at the end, I said find delta H of all of these and then add to find the total energy required for the reaction to happen, the state changes. So you're going to do each calculation individually, and to find that total delta H, you're going to add them all together, and it's going to be in joules or kilojoules. So that's how you do the heat and changes of state one. I hope that makes sense, because it's kind of an earful, but if you just remember, make sure you draw your little graph out, and you just kind of remember that you do Q equals MCAT, then delta H all the way to E. I think you will be okay, which I can work one of these out if you want, but I hope that helps as is. And then we have enthalpy change. I'm not sure if this will be one of them. I can't remember, but this one was number 8 on the study guide, the combustion of methane, CH4. And what you do is you just do dimensional analysis for this one. We are given the delta H, 890 kilojoules, and when you have this energy or heat as a product, it's an exothermic reaction, so it has to be negative. So we were given 10 grams of methane, go to moles, and then the very last box is negative 890. When you do the math on that, you get a delta H of negative 555. So this reaction took negative 555 kilojoules to combust methane. So that's what you're trying to find for that one. And then the last two I'm going to do have to do with Hess's law. For Hess's law, I know it's really complicated. It's kind of a lot. Make sure when you're going through, you just start with whatever you're trying to find. So if you're trying to find 2N2 plus 5O2 goes to N2O5, start with, flipping the second reaction so you have N2O5 as the products, that type of thing. And I can work another one of those out. What I have to do sometimes is write down what I did so I know what I have to have at the very end, to add all those up to get delta H. And then we have finally what did I say I was going to do? Okay, I'm going to do one of the products minus reactants problems. So this one is on the extra practice. It's station 6. It's Hess's Law shortcut. So it gives you the delta H's above, so you don't have to use your appendix. But the equation is C5H12 plus 8O2 yields 5CO2 plus 6H2O. And it specifically says water as a gas. You have to make sure you're looking at the states too, because there are different delta H's for different states. So I just don't want anyone to lose easy points because they're not paying attention to the state symbol. So we're trying to find delta H combustion for this problem. We do products minus reactants. And I don't think this is going to be a free response problem, but definitely a multiple choice problem, and I want you to get those points. So we're doing delta H. So the delta H of carbon dioxide is 393.5 plus 6, and then we have negative 241.8, which is the delta H of water vapor, it's the gas, minus negative 276. The reason why we only have C5H12 as our writing it as our reactant is because any element in its natural state, which really are the diatomics, their delta H is 0 because it's in its natural state. It doesn't take any energy, I guess, to get to that point. That's how I would say it. So we did our products minus our reactant, and you have to make sure, so this is the delta H for 1 mole. So if it has a coefficient of 5, then you would do 5 times that delta H. Coefficient of 6, 6 times that delta H. And then we get a delta H of negative 3,245.2 kilojoules per mole for that one. So that's all I have. Oh, and make sure you know that this delta H with the F and the little bubble, that means standard heat of formation. So just make sure you know that. And that's pretty much all I have to review. But if you have any questions, I would make sure you know these fast facts that I sent you. If you have any questions or want me to work any of them out in particular, then just let me know. So that's all I have.